In this video, we solve problem 2.6.11 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to use the method for solving homogeneous equations to solve the following differential equation. And this time they're referring to homogeneous polar differential equations. Note that this is a polynomial function in x and y, and this term is degree 2, and this term has degree 2. Remember, the degree is just the sum of the exponents if you're talking about a polynomial function. Since this is degree 2 and this is degree 2, the sum of those is a degree 2 homogeneous function. This is a degree 2 homogeneous function as well. That tells us that the differential equation is homogeneous polar. If they didn't already tell us that it was homogeneous polar, we could verify that, or we might think that that's probably what we're looking at just by looking at those degrees, the degrees of these two guys and then the degree of that guy. Now they want us to find they say the general solution in the form y equals a function of x. I guess it's probably not the general solution since this is a nonlinear differential equation, but it is likely to be a family or a family of solutions. And they want us to write it in this form. So they're basically saying when you're done, solve for y and write y equals some function of x over here. Now, most of the time, if we're solving a homogeneous polar differential equation, the first thing we want to do is verify that it's homogeneous polar. We're not going to do that this time because they tell us that it's homogeneous polar. So we're going to start right here. We want to write this homogeneous polar differential equation in the form dy dx, it's the derivative of our dependent variable with respect to our independent variable, is a function of y over x. In order to make that happen, I'm going to keep this x squared dy on this side, and then I'm going to subtract 13y squared times dx from both sides. So when I subtract 13y squared times dx from both sides, it's gone over here, and I have a negative 13y squared times dx. And then to get rid of this negative xy times dx, I'm going to add that to both sides. When I add that to both sides, I have a positive xy times dx over here. So if we start there, we have that. Now we're trying to make it look like this. So we will divide both sides by x squared, and we'll divide both sides by dx. Now I have dy over dx, which happens to be dy dx, and by the definition of those differentials, and that's equal to this function of x and y. Now we want to write it in this form. We want to see expressions involving, or an expression involving y over x. We want that to be the quantity that we're manipulating. So we will take each of these terms and divide them by x squared, because when we do that, we get something that looks like this. xy divided by x squared simplifies. One of the x's will be gone, and we'll be left with a y over x. So the y over x is right there. And then I have a negative 13y squared over x squared. If I factor out that negative 13 and use this property, I can write that as y squared, or y squared over x squared can be written as y over x quantity squared. So now this is a function of y over x. If I let v equal y over x, this is just a v minus 13 times v squared. That's what we want. We want this to be a function of v only, where v is equal to y over x. If you had any y by itself or any x by itself, that could not be just written, and this expression could not be written just in terms of v, that would tell us that we're either not looking at a homogeneous polar equation or we're not done yet. Okay, so we've written the equation in this way. From here, the way we solve it is we write this entire differential equation now in terms of v and x. So we want to let v equal y over x. Then we're going to replace y over x in the differential equation with v. And then we're going to replace dy dx with the result of the product rule. So let me show you how that's done. We're letting v equal y divided by x. Then if we multiply both sides by x, we get y equals v times x, where v is a function of x. And then if we compute dy dx using the product rule, where this is our first function and this is our second function, we get derivative of the first times the second plus derivative of the second times the first. So we're going to replace dy dx with dv dx times x plus v, and that again is due to the product rule. So we're replacing this with this. And on the right-hand side, we're going to write that in terms of v only. So we have v minus 13 times v squared. And then we solve this separable differential equation. This differential equation will always be separable in v and x. So first I would subtract v from both sides. That's nice. The v's are gone. And you end up with dv dx times x equals negative 13v squared. Now, we have this x function here and a dx in the denominator. In order to change that, so we've got a dx multiplying a function of x, we're going to take the reciprocal of both sides. If this is equal to this, then if we flip these, that's going to equal this. You can take the reciprocal of that and take the reciprocal of that. Now, I also happen to switch them that way, but that was just a personal preference. You can multiply in any order you want, so that's legal. Okay, and now we want all the v's over here, so we'll multiply both sides by dv. You can think of those as reducing. And I would factor out the negative 1/13 and bring up that v to the numerator and write it like that. So we got all the x's on one side and v's on the other, and we went from here to here by taking the reciprocal of both sides. And then you just anti-differentiate each side with respect to the variable that's there. The antiderivative of 1 over x is natural log of the absolute value of x. Then we bring the negative 1/13 down. Then here we're going to add 1 to the exponent and then divide by the new exponent. Don't forget to add c. And of course, dividing by negative 1 is the same as multiplying by negative 1. So we have actually positive 1/13 times v to the negative 1, which is 1 over v plus c. Now, we don't want an answer in terms of v and x. We want an answer in terms of y and x. So we need to back substitute. Remember, back substituting is just replacing. You're going to replace v with whatever it was in terms of y and x. Remember, v was y over x. The reciprocal of y over x, that's 1 over v in this case, is x over y. And so we would be done if they wanted an implicit solution, but they don't want an implicit solution. They want an explicit solution. They want us to isolate y. So we just have to do a little bit of algebra in order to get y by itself here. I would recommend multiplying both sides by, let's say, 13y. That will clear the fractions on both sides. Oops. So we have 13y times the natural log of the absolute value of x on one side. Equals, we had this 1/13 times x over y plus c. When we multiply this side by 13y, the 13y here and the 13y there will reduce, and so we'll just have x. And 13 c times y, that's what we get here. I would just call that a different c times y. So c1 is just 13 times c. We're still trying to get y by itself. So I would subtract c1 times y from both sides in order to get all of the y's on the left-hand side. Because that's going to get us closer to solving for y. Then we'll factor out the y. And then divide by this expression so that y is by itself. And if you wanted, you could say that negative c1 is just positive c2. And so you have that. And that is a family of solutions to our differential equation. Now, this will be undefined whenever the denominator is 0, and the denominator will be 0 whenever 13 times the natural log of the absolute value of x is equal to c2. That's going to happen at some point. Natural log of x takes on all real number values. Natural log of the absolute value of x can be any number between negative infinity and infinity. That's the range of this function. So there is a value of x for which this will cancel with that. That would be the x value that is not allowed in the domain of y, and the maximal interval of existence of the solution to the differential equation would go from that value either to infinity or from negative infinity to that value, depending on what our initial condition was. And we actually don't have an initial condition in this case, but if we did, we would use the initial condition to choose the appropriate interval of existence. So that is how we do that. Just as a brief recap, when you're solving a homogeneous polar equation, you need to write the differential equation in this form. So you need dy dx on one side, and then you need a function of y over x on the other side. And that often involves just moving terms from the left-hand side to the right-hand side. And there's a lot of multiplying and dividing by differentials like dx, and also by functions of x and y. So you end up over here, and then you have to simplify this. So it's a function of y over x alone. In this case, the easiest way to do that was to take each of these terms and divide by x squared. Another option would be to divide the numerator by x squared and the denominator by x squared. But when you do that, you end up with a 1 in the denominator, which gives you the same result. And then we had to use some exponent properties. We had to remember that this was equal to this to see that that y squared over x squared is that. So we get here, and then the idea is to take this and write it entirely in terms of v and x through making substitutions. We let v be y over x. So this is our v minus 13v squared. And then we say, if v is y over x, well, what does dy dx have to be? Well, we can find that by first solving for y by multiplying both sides of this equation by x, and then using the product rule on this, where v is a function of x, to find dy dx in terms of v and x. And then you just substitute. You replace this with this, and you replace this with v minus 13v squared. And then this differential equation will always be separable. So you separate the variables. Usually the first thing you do is subtract that v, because this is going to be your dy dx every time. Subtract the v from both sides. You want to write this side as a single fraction and this side as a single fraction. This time we were lucky, it was already written that way. And then once both sides are written as fractions, you want to take the reciprocal of both sides so that your dx is in the numerator and it's multiplied by that 1 over x over here. Then you multiply by dv, and that's enough to separate the variables. Then you just anti-differentiate and back substitute. And then because they wanted us to get y by itself, we had to do a little bit of algebra. And for us, for this particular problem, the algebra that was required was getting that 13y out of the denominator. We needed y in the numerator. So we multiplied both sides by 13y. Then we distributed. We had a y term on this side and a y term on that side. And then we solved that the way you would solve any linear equation. If I had like a 3x over here and a 5x over here in a pre-calculus class, I would just subtract the 5x from both sides to get all the x's on one side. It's the same thing we're doing here. I want to get this on the side with the y's, so I subtract that from both sides. I factor out the y, and then I've got y times something equals x. So to get y by itself, we divide to undo the multiplication. And that got us here. And the interval of existence excludes the x value that causes that denominator to be 0. And either goes to infinity or negative infinity, either on the left or the right, depending on the initial condition. But since we didn't have an initial condition, we're not going to worry about that this time.